So we did this last time to reactance as a complex function. Okay, so let me start with the voltage Vt equals B0 cosine omega t. So what happens in the complex notation? In complex notation, you have B0 e to the j omega t. So instead of I, we replace this by j because we want to avoid confusion with the current. So now let's do the capacitor current. Now what happens in the capacitor? Number one, let's do capacitor. In the case of capacitor, what do you get? I is dq over dt. And in the capacitor, what is your Q? Q equals CV. C equals Q over V, right? So remember, this gives me this. So then C is constant. You can pull it out. So V over dt. So what is the derivative of this guy? So B is this, right? What is the derivative of this V? V0, right? V0 is constant. Then you have j omega. Then e to the j omega t. That's the derivative, right? So can I write this guy, these three combined? See, these three guys is exactly same as this, Vt. Okay, so I equals C, I can say, right, J C omega Vt, right? That's my I. Now, I want to write it in this form now. So V equals Ri, right? So what is your I? I equals V over R. Then how do I write this guy in terms of V over R? So Vt is V. In R, this guy has to be written in the form of R, so which is this way, right? Okay, so this is R now. So we don't call it R, but we call it ZC. Okay, so Vt over GC. Instead of R, you have ZC here. So your GC is 1 over J omega C, right? So, but the thing is, we write in this way, we A plus IB or JB, right? We write the complex number in this form. Your J is on the bottom, okay? But the J has to be on the top, okay? So because A plus JB, not on the bottom. So you have to somehow bring that J to the top. So can I write that J1 as negative J square? I can write this 1 as a negative J square. So then I can cancel this J and J, which is negative J over omega C. Does it make sense? This is your GC. Again, now what is my, you find your GC. So the thing is, you found the GC, you found your GC is negative J over omega C. Okay, keep this in mind. Now, what is your I? I is CB0 omega J e to the J omega T, right? That's your I. Let me change the color, it's too red. A lot of red, okay. That's what I'm talking about, this guy here. This is my I. So J, as we did before, right? J can be written as e to the J pi over 2. Then your I will be CB0 omega. J will be e to the J pi over 2 e to the J omega T. So then you can combine these two guys, CB0 omega. And this guy is, help me here, J omega T plus pi over 2. Okay, so this is your I. What is your B? B equals B0 e to the j omega t. So what is the argument here? Omega t. What is the argument here? Omega t plus pi over 2, which is bigger. This guy is bigger, right? It means current I leads, meaning voltage lags. V lags I. So we did this last time, okay, until this. Okay. All right, so, okay, now let me continue for the inductor now. So what is for the inductor? We did for the capacitor, right? What is for the inductor? For inductor, I'll begin because what is the relationship between voltage and current in the inductor? Vt equals L di over dt, right? That's the voltage for the inductor. Then you have to do the derivative of I. So that's why you have to consider I equals I0 e to the j omega t minus pi over 2. That's your I. Then how do you differentiate di? Di will be, so help me here. L is L. What is the di over dt? I0, right? Then here you have e to the j omega t minus pi over 2. Then you have to do the derivative of this guy, right? See the chain rule? J omega. Again, this j can be written as what? J can be written as, remember, j can be written as e to the j pi over 2, right? So that's why I am going to write this guy as e to the j pi over 2, then e to the j omega t minus pi over 2. Then if you add them together, what do you get? Li0 omega, and this guy is e j omega t minus pi over 2 plus pi over 2. So this pi over 2 cancel out. You are left with Li0 omega e to the j omega t. So far so good. Now this guy is called B0 now. This is B0 actually, B0 e to the j omega t. So you started with this here. This is your argument here, right? So what is the argument of this guy here? This is the argument. Which one is bigger? Omega t is bigger. That's why V leads I. Okay. So we did the inductor. We did the capacitor. Now what is the, so this is the thing. Now the thing is, so here, so your B is this, right? Your B is this. So what is your GL? Help me here. What is your impedance, GL? So what is this guy here? What is this guy? Help me, guys. You have to find ZL. What is this guy? Can somebody help me?
I.
This is IT, right? Or I. You can write IT here. This is IT, right? So thank you. So then I want to write V equals RI or GI, whatever I call it. So V equals GI. So what is this? Is I. What must be this guy? This guy should be G. So GL will be J L omega. So now let's do the conclusion. Oops. Let's make the conclusion here. What is your GC from previous slide? If you remember, what is your GC? GC is negative J over omega C. This is your GL. What is your GR? GR is simply R, by the way, okay? There is nothing there. So then what is the total G, which is called GT, or you simply write Z equals GC plus GL plus GR. So which is GC is negative J over omega C. GL is JL omega plus R. That's your total impedance. Right? Does it make sense? Question here. Please comment. At least you could say awesome job. Please say something.
Awesome
Amazing.
job.
You nailed it.
Okay. I'm feeling sleepy. Wake me up, guys. Thank you.
It's hard to wake you up when I'm also sleepy.
Yeah. It's too early, right? Plus, so how do I rearrange this guy? J L omega minus 1 over omega C. That's my G, right? Okay, that's the, see? I rewrote this guy on the top. All right, so this is what we have now. So now let's do the generalized Ohm's law.
Pardon me, Professor.
Please.
What is the purpose of all these Z's?
Oh, because our goal is, yeah, that's a very good question. Remember, when we write in terms of complex numbers makes our life less complex, right? That's the thing. Complex numbers make it less complex. Remember, we want everything in complex number, remember? So if you, let's say if you, so what is the thing? So cosine theta plus I sine theta. How do you write this guy? E to the I theta? Right? So see, instead of doing this, if you have complex notation, then you can, instead of, you know, for instance, if you just want to, I'll give you just one example, very easy on this example. So if we, instead of doing derivative or integration here, you just do the integration here or derivative here, which is way easier because derivative of e to the x is e to the x. Derivative of e to the x is e to the x. See, just close your eyes, you know, it doesn't change anything, right? That's so cool. That's why we love complex numbers, because complex number can be written in terms of, in this form. Suppose this is a complex number, right? This is a complex number. Then we can write this complex number in this form, which is so cool. That's why we are so excited and we are crazy about expressing everything in complex number now.
I see. Okay, thank you.
All right. All right. So that's why I'm going to write the Ohm's law in complex form also because I'm so excited. I'm crazy now. Because I love complex number, I want to do everything in complex now. That's so cool. So what is your Ohm's law now? Your Ohm's law will be I equals B over, instead of R, now we are talking about complex now, that's why I call it G. So remember how do you write the complex number? How you can write the complex number? Complex number can be written as any complex number. This guy can be written as, yeah, this guy. So suppose you have a here, right? Suppose A cosine theta, this one. How do you write this guy? A, do you see it? Let me rewrite it. I can do that. A cosine theta plus IA sine theta can be written as A e to the I theta. This is the complex number, right? This is a complex number. So any complex number can be written. This is a complex, let's say I call it P. P is a complex number. Any complex number can be written in this form. Any. Okay. So this is the, so that's why, so I know my V, right? So what is my V? So my V, how do you write my V? V equals V0, see, in this form, e to the j omega t, right? That's my V. So V0 is A, and this is E I theta. See, I have V in this form now because any complex number can be written in terms of, in this form. Okay, in this form. So then similarly, if any can be written, then how about Z? Z also can be in this form. There is no doubt, right? Z. So I call it Z absolute value. You know what that means? What is this A? What is this A? A is absolute value, okay? By the way. So what does this mean? Suppose you have a vector A. This is your A, right? This is theta. Then this A means, they say this is 5. So absolute value meaning, how do you find, what is the length of the vector? Help me. A equals x square plus y square, right? So it always is positive, right? It's always positive. That's why I call it magnitude, okay? I take the absolute value because my length is always positive. That's why. So this A is positive. So my Z can be written as Z e to the j phi. Can I write like this? Please say yes, no, maybe.
I mean, it looks good to me.
Okay,
This
thank
is
you.
America. It's a free country. You can do whatever you want.
But I do have one question.
Please.
So, are we getting the variables of, or the exponents above E? Are those from our previous equations that we just did?
Or this guy?
Say like the JWT and the J Greek symbol.
Phi.
Yeah. Where are we getting those from? Just set equations that we know.
Okay. Okay, let me, one more thing. Any complex number, so let's say my complex number is P, right? So this complex number can be written in terms of P absolute value e to the I theta. Any complex number. Okay. Now, so it means I should be able to write Z in this form. I should be able to write V in this form also. So we have been writing V in this form from the previous slide, right? We know this V is written in this form already, right? We have already written V in this form. We have seen that in the previous slide also, right? So I don't think we have a question here. The thing is, how did I write this G as this? So now Because since I can write any complex number in this form, and my z is also complex number, how do I know? Because this is my z. See, this is the complex number. That's why I can write z in this way also, which is z equals absolute value of z, then e to the j phi. Instead of theta, I chose phi. I could have chosen theta, that's fine too. Did I answer your question?
Yeah, that helped. Thank you.
All right. Okay, now, so our goal is to write my I in terms of complex this thing, right? So let's do that. So what is your I then? Your I is V0 e to the j omega t divided by z e to the j phi. Okay, so V0 over z absolute value. So j omega t minus phi. This is my I. So now what is my current now? Your current is, so how do I rewrite this guy? Let me rewrite this guy. Z equal, okay, this equals, how do I rewrite this guy in terms of cosine and sine? Can I write this guy like this? You know what? I made a mistake here. Minus phi. Plus j omega t minus phi. So then remember we changed this. So our signal is not this, right? Our signal is just the real part, right? That's why my I will be, finally, my I will be V0 G cosine omega t. So for the calculation, I took the help of E, okay, for the calculation. And finally, I can convert this guy to this and choose whatever I want. My thing is just cosine. Now, how do you know which one leads or which one lags? So so now you started the voltage is what? Now, can you guys tell me which one leads, which one lags? Compare these two guys. Compare these two guys and tell me, does the current lags or voltage lags?
The voltage leads.
Voltage leads, right? Okay. So thank you. So this is a very good guess. The thing is, we don't know the sign of phi. Phi could be negative or positive. That's the thing. Phi could be either positive or negative. So if phi is, let's say, negative 90, right? Then my equation becomes, the argument here becomes j omega t plus pi over 2. So depending on the sign of phi, so we'll decide whether I leads or I lags. Okay, that's why we have to pay attention to, because phi could take any sign, because we're not saying that phi is positive, right? Phi could be negative too. If phi is negative, then current leads. If phi is negative, then as you said, voltage leads. Okay. Now I have one more question here. So what is your So I said Z is this, right? Z is this guy. Okay, Z is this guy. How do you find this guy here then? How do you find this Z? Z absolute value. Your Z is this, right? See, your Z is this. But how are the absolute value of Z? How do you find the absolute value of Z from there? If you have a complex variable, this is your A, this is your AX, this is your AY. So how do you find A? The length of this vector. Length of this vector. AX squared plus AY squared. Okay. But when you do, how do you find, in the same way, how do you find the G absolute value? G absolute value is always found like this. So G absolute value, so G equals this. G star. That's your Z. That's how you figure out. So what is your G here? Help me here. What is your Z? R plus J L omega minus omega over C. How do you find Z star? This is your Z. How do you find Z star? Z star will be R minus J L omega minus 1 over omega C. That's your G star. G star meaning just change the sign of imaginary part. Change, okay? If it is positive, we have negative here. If you have negative here, instead, you will have positive here. Just change. That's how you find the G star. Change the sign of imaginary part, not the real part. This is real part, this is imaginary part. The sign of imaginary part. That's how you get the G star, okay? Then what do you get here? See, A plus B, A minus B, right? A square minus B square. J square L omega 1 over omega C square. What is negative J square? R square plus, right? This is minus 1 and minus plus. So that's why you have L omega minus omega C whole square. See, it's again, this is of the form of AX square. This is of the form of AY square. Exactly as we did here. Okay, this is how you find the Z absolute value. Guys, question here, please. Please, any comment? All right, so let's do the impedance combination, okay? How do you do the impedance combination? So this is very easy, as you have seen this in the previous, in the case of resistance, right? We have seen this already. So,
Professor,
yes, please.
I'm sorry, just for a second. Could you go back real quick? Oh, so the imaginary number winds up disappearing?
Yeah, because this J square is what? Because J, what is the definition of J? 1 over omega C. 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 1 over J is,
-1, right?
yeah. So what
Square.
is it?
Okay.
So J square happens to be -1. So this J square is -1. This negative and negative makes positive.
Okay. Thank you very much.
All right. So let's do the impedance combination. Okay. Suppose you have the two impedances, right? G1 and G2. If they are connected in series, then what is the total impedance? Total impedance is G1 plus G2. As in the case of resistor. So remember, you have in the resistor R equivalent, equals to R1 plus R2 if they are in series. In the same way, impedance also follow the same rule. And similarly, if we are parallel, it's the same rule again. Okay, so these two are in parallel, and the equivalent is given by this formula again. Okay, and the voltage divider also same rule again. Voltage divider B out equals, it's the same rule again. See, if you want to find the voltage across here, then G2 over G1 G2, right? G2 over G1 G2, then B in. So that's the voltage. It's the same thing again. Okay, it's the, you just replace R by Z. That's all. It's the same rule again. Okay. Okay. Now the thing is, now I'm going to solve the LR circuit. Okay. So we'll do one at a time now. LR, starting from LR. The circuit having yeah, I think this is just the, just the one example of LR circuit. Okay. So I have the LR circuit. The inductance is here and the R is here. Then what is the current flowing in this conductor in the circuit? Ohm's law. If this is BT, right? If this is BT, what does the Ohm's law tell you? Ohm's law is B over GT, right? Total resistance in the circuit. Okay. So what is the total resistance in the circuit? One from R. This is R. And then you have to add the impedance from L. So which is J omega L. Okay. So this guy also can be written as in this form, right? Remember, anything can be written as Z e to the J theta, right? We can write it in this form. So that's how you can write this G. So if you know this guy, how do you find G? If you know this guy, how do you find the magnitude of this guy? R square plus omega square L square. That's what we did before, right? Okay. Then you have e to the J theta. So here. Now, if you consider your B is, because remember our BT over Z, right? GT. So if your BT is this, as we did before, right? And your GT is this now. Okay. Then how do you find the theta? So this theta, right? We have theta here. See, this is theta. So how do you find the theta then? What is theta? Where does that come from? This theta comes from this. So this is GT, right? If this is your GT, absolute value. Oops, let me simply call GT. If it is GT, then what is your R? Real part is R, and imaginary part is J omega L. That's what this means. How do you find the theta? This theta. This theta. This is this theta, right? So meaning, what is theta? This is the imaginary axis, right? J axis. So what is theta then? Theta is the length of this guy, right? What is the length of this guy? J omega L. How do you find the length? length of this guy, I'm talking about length of this guy is omega L J minus omega J L square root, right? Remember? That's what you do. G star, right? That's what you do. Then what you get here, if you multiply this together, what do you get? This guy and this guy becomes J square, and this minus and J square plus J square, then omega L square, then take the square root, you simply get omega L. Okay? You don't have to do all this every time, but just to show you how you get it. So that's my omega L. Y is omega L, and R is your X. So how do you find theta? Tangent of theta equals omega L times R. Then what is theta then? Your theta is inverse tangent omega L over R. That's what it is. Then you can plug this in here. So if you want, so you can simply plug this in. So let me do it here. So your I is now V0 e to the j omega t divided by gt. Help me here. R is square plus omega is square L is square e to the j theta. Then you can rewrite this guy as, you can bring it up, right? Up there. So how do you do that? You just put negative sign in front, right? So minus negative meaning theta here. So like this. Okay, that's how you do it. So this is your I. Okay, you got the I, right? I got the I in the, so you solve the circuit already. So you have the I, meaning if you know L, R, and VT, then you can find I, which is VT is this guy, right? Which is V0 j omega t, and you are given L and R. That's what it is. How about omega? Omega also given. Then theta, right? Theta can be found in this way. So it means you found I. Okay. Let me find the voltage across the resistor then. So what is the voltage across this guy here? Here, what is the voltage across this guy? What is VR? So what is VR? VR equals RI, right? Ohm's law. What is your I? I is this. Then multiply by R, meaning this. That's your okay. Now I can call this, because I'm talking about VR, right? So let's write VR in terms of VR, then e to the something, right? Remember, I can write everything in this form. I don't know, phi, e to the phi. My phi here is this. My phi here is, this is my phi. Remember, this guy is my phi. You see this, right? This circle, this is my phi. So this is my phi. This guy is done, right? And this guy happens to be VR. Absolute value, right? This is my VR. Then what you have here is this. Your VR is what? VR is your VR. Okay, VR is your VR is this VR. This VR is VR absolute value. VR absolute value. Then this for this guy here, right? This guy e to the j omega t minus theta. So what is my VR then? VR is VR is this guy, V0 R, V0 R, right? V0 R, help me here, I'm lost. R square plus omega square, L square. That's my, now, how do you find VR over V0 from here? I want to find VR over V0, meaning I can write this guy as this, right? I can write this guy as this. So this is the absolute value, right? Where, yeah. So I can write this way. So divide both sides by V0. What do you get? This V0 cancel out. Then you are left with VR over V0 equals R over this guy here. That's it. The thing is, why do I need this ratio? Right? Why do I need VR over V0? That might be the question, right? Then I want to compare I want to compare the value of normalized VR with respect to V0. Okay, that's what I'm trying to do. I want to compare the amplitude here with the source amplitude. This is my B0. This is my VR. I want to compare these two. Okay. Now, if we plot this guy as a function of omega, if you plot, suppose this is your y and this is your x. Remember, if you plot this omega versus VR over V0. If you plot it, then what kind of graph do you get? You'll get this kind of graph. Sorry, not the omega. Omega divided by LR, okay? This versus this. This is L over R is just constant, right? So only thing that varies with omega, okay? So we are just normalizing with respect to L over R, that's all. So then this guy looks like this. If you plot the maybe Excel, or you can use MATLAB or Octave or whatever you use the software, any software. If you plot the graph, you will see like this. So what do you make of this this graph? When omega is zero, look at this. When omega is zero, this is zero, right? What is the value of this guy? 1. What happens if this guy omega is infinity? Infinity means very, very far away, right? Infinity. It looks like this guy goes to 0, right? When omega is infinity, this goes to 0. When this is 0, this goes to 1. When this is infinity, this goes to 0. Okay? So meaning this LR circuit, right? This is the LR circuit. See, we call it LR circuit. LR circuit act as low pass filter. So we'll talk about filter in chapter 7, okay? We'll talk about the filter behavior in chapter 7. But for now, just I want to introduce a little bit about it. So what is low pass filter? A filter that filters which passes the low frequency signal and blocks the higher frequency signal. See, it's blocking all the signal. Higher frequency, these are higher frequency is blocked. It's almost 0, right? See, higher frequency is blocked. 0 means blocked. See, it's trying to be 0 here in this area. See, in this area it's almost 0. Means it blocks the higher frequency. It only shows the lower frequency, this region. So something, it shows just something and blocks the other thing. What is that called? Filter, right? Suppose you have a filter in chemistry lab. You have a filter paper, right? You have filter paper. Then it filters, it lets, the water, whatever, it goes down, right? So, and it filters this kind of, I don't know what do you call it, any residue or something, residue. Okay, that's called filter, right? So this also acts like the similar filter because it blocks the higher frequency. It is blocked because it is 0. 0 is blocked, but it lets it lets the low frequency signal pass through it. So that's why this behave like a filter. By the way, this is called low pass filter because it lets the low frequency pass through it. That's why we call it low pass filter. But in detail, we'll talk about it in chapter 7. Guys, so far so good. I'm not sure what you guys are. I've just kept talking. Please help me to understand. Any questions so far?
Following along perfectly.
Austin, did you see something?
Then following along perfectly.
Okay, very good. Okay, now let's do the dissipated power here. The power lost, right? Suppose power lost in the suppose LCR circuit, right? Because so you have a AC source, right? What are the 3 components you can have? You can have resistor, you can have inductor, right? And you can have capacitor. That's the 3 things you can have. This is resistor, this is inductor, this is capacitor, right? So what is the power lost in the circuit? Okay, let's figure that out. What I meant here is whatever power given by this source, okay, so what I meant is this. Some power is lost when, okay, that's what I meant. So when you have, this is the source of power, right? So when this guy flow through the circuit, some power is lost in the circuit. That's what I'm trying to make you understand, okay? So, so what is power first? What is power? Power is the average power. By the way, this is average. When I say average, it's always 1 over T is, 0 to T. That's the thing. It's always this, right? When I say average, this thing should come in your mind. When I say average, 1 over T integration of 0 to T. That's the meaning of this. This is what average is, okay? That's what you learn in calculus 1 or calculus 2. Average meaning 1 over 2 integration 0 to T. That's the average. Average of what? Power, right? What is power? Power is IB. That's the power, right? DT. That's the average power. That, by definition, this is the average power. So if you plug in the value of I, in the B equals, what is the B? B, remember in the Ohm's law, you have this B's, oops. Oh, this is so messy. Remember in the Ohm's law, you have some V and I's, right? So you have B, this is B, and this is I, remember? So plug this in here, plug this in here. If you plug this in here and do the integration, you end up getting this formula, okay? So this takes like almost a 1-page derivation, okay? So it's 1 page. So I have done it, I'll upload it on the Moodle, okay? I'm not going to derive it now because I don't think this is difficult to understand. This is just chapter, this is just the calculus, okay? So if I give you how we do it, how I do it, so you should be able to follow it, okay? Because this is math, this is not electronics, okay? Because you have done calculus 1 already, so you should follow that, okay? So I'll post it on the Moodle. I'm not going to derive it now, okay? So if we, this guy, if we plug in the values and then we'll get to this relation. This is the final form, okay? So here, what are these things? So B0 That's the amplitude. This is the G, right? This is the, what is Z? Z is again, what is G? Your G is, help me, R square plus, you know what G is, right? So what is your GR? GR is R. GL is, oh, GL is given here. See, GL is this, and GC is this, right? You know what your G is, okay? Now, if you have the circuit, let's say, I'm not talk about the resistor now, okay? Let's say one at a time. So resistor, let's talk about resistor. Then I'll talk about the inductor. Then I'll talk about the capacitor, okay? One at a time. So for the resistor, what is the G? G is simply R. It doesn't have imaginary part, right? So G plus J0, right? Because ZR is simply R, meaning imaginary part is 0, okay? So then how do you find theta here? What is theta for the GR? Because ZR can be written as ZR e to the I theta, right? Remember? We can always write that. So what is your GR? GR is simply R. Then what is your theta then? What is your theta? So find theta from here. What do you get? What is your theta here? Theta is inverse tangent 0 over R. You see that? 0 over R. That's your theta, inverse tangent, which means 0. This guy is 0. Means e to the 0 is 1, right? Simply. Okay. Then how do you plug this in here? Now let's plug this in here. Let's plug this in this formula that we derived. You know, quote unquote derived, right? So what is your cosine theta then? Cosine theta is cosine 0, right? Cosine 0 is 1. This guy happens to be 1. Then V0 is square over 2Z, right? So what is your Z? Z is simply R. So that's why V0 is square over 2R. Does it make sense? That's what you have here. Okay. All right. So what is the formula for power in the case of DC circuit? Do you remember? In physics 111, how do you do the power? Power is IB, you know, I is a B over R, right? Then V. Then B square over R. Remember, this is the power. But here, what did you get? In the case of DC, you have this. In the case of AC, you got this. V0 is square over 2R, not R. Do you see that? In the case of AC, you got V0 square over 2R instead of V0 square over R. Okay. Now the thing is, what happens is, so V0 square over 2. So this is my B. So let me introduce one quantity, B RMS. What is the square of this guy? Help me. What is my B RMS square? Can I say B0 over 2? Meaning my B0 square over 2 is actually B RMS square. That's why I can write this guy as B RMS square over R, which is exactly similar to this guy. Okay. So the thing is, so in the AC we measure VRMS. In the AC, because AC is fluctuating, right? So you don't take the highest one, you don't take the lowest one. You take something in between. What is that called? VRMS. Okay, most of the device are multimeter, right? Remember we have multimeter in the lab. That multimeter reads this VRMS. When you measure your AC voltage, your multimeter does not fluctuate like this, right? It doesn't fluctuate like AC. It will give you a constant value. That constant value is VRMS. Now let's look at the thing. Now, so this is the power lost in the circuit by the resistor. Average power dissipated in the circuit by resistor is this guy. It means all the power, delivered power is dissipated, all the power. Because source delivers V square over R and everything is done. Everything is dissipated. All the power delivered by the source is dissipated in the resistor. How about the inductor now? What happens in the inductor? So your inductor is ZL equals J omega L, right? So then what is we are using this formula again. We are using this formula again. So what is theta in the case of inductor? So this is my Z, right? So in real part is 0. Real part is 0. 0 plus J omega L. And how do you find theta? This guy over this guy, right? That's what it is. So what is this theta then? Your theta is pi over 2. So then your cosine here is, this guy is cosine pi over 2. What is cosine pi over 2? Guys, help me here. What is cosine pi over 2? Zero, right? So entire thing becomes 0 then. V average is 0. So it means inductor, they don't dissipate energy. Instead, they store energy. Remember, you have been talking energy storage by the we have been talking energy storage by the inductor in physics 112. Okay, so it means inductor do not dissipate energy, they instead store energy. How about the capacitor? Capacitor is GC equals this, right? So what is the theta here? The real part is again 0. So then what is the theta? Theta is this. The negative pi over 2. What is cosine negative pi over 2? Again 0. That's why again the capacitor do not dissipate the energy. In other words, they store the energy rather. So only component that dissipate energy is the resistor. Other two, they store energy. Guys, I keep talking. Please question here. Yes, no, maybe, kind of, not really.
I think I got it.
Yeah, very good. So normally when you guys don't have question, it means you understand everything or you don't understand anything. Okay. So, Austin, did you see something?
I said both.
Both?
We both understand it and don't understand it at the same time. So
Okay. So now let's talk about the voltage source versus current source. There are two kinds of sources. One is voltage source, the other one is current source. I'm sure you guys are familiar with the voltage source. Remember, we call it battery, right? That's the voltage source. I don't think you guys have any problem with understanding voltage source. A battery is a voltage source. Or you can represent this way also, okay? It's the same thing. Plus minus, make the circle, plus minus, and write V. Or you can do, you know, this is small line, the longer line, the longer line, short line, long, you know, depending on how many batteries you have. And the longer is positive, and the shorter is negative. So this is all, this is battery. So both of them are voltage source. It's the either word. You can either word notation. But by the way, what is voltage source then? We know how to represent it. This is how you represent, but what is the definition? Ideally, a voltage source provides constant voltage to the circuit. If some source provides constant volt to the circuit, that's called voltage source. Current can go up and down depending on the demand of the rest of the circuit, but the voltage remains same all the time, okay? That kind of source is called voltage source. However, the current source is the opposite. For the constant current source, the current does not change, okay? How do you represent your current source? For voltage source, you represent by this, right? For the current source, instead of writing plus and minus, you write the arrow like this. But remember, this arrow, for this, the arrow has to be this way. It cannot be this way. Okay? So, but if the thing is like this, if the thing is like this, then arrow is like this. Okay? So arrow in the direction of positive. Why I'm saying this? Because we can change the voltage source to current source. So in that case, we have to pay attention. You have to pay attention to that plus and minus. Wherever plus is, the arrow goes that way. So that's what I meant. So you can transfer one source to the other source, okay? Suppose you have a voltage source here. So what do you have here? You have voltage source here, you have the resistor here, then you have another resistor here. Okay, these consist of one circuit here, right? This is the loop. You have three things in a loop: voltage source, RS, and RL. Okay, so how do you convert? This is definitely voltage source, right? This is your voltage source. So how do you convert this voltage source to current source? You can do that, okay? That's the good news. How do you do that? Just put this guy, what is this guy? This RS is in series, right? This RS is in series with this guy, in series. Now, if you put this guy in parallel right here, see here, move this RS to here in parallel, like this. Then this guy becomes current source. This ES no longer remains ES, rather that becomes IS, because this voltage source is now current source. Remember the arrow? We have the arrow towards the plus sign. See, that's what it is. Okay, and what is the current? What is the current given by this source then? If it is current source, right, it should provide some current. Then what is the current then? The current is given by this E divided by this R. Remember the Ohm's law? E over RS is the IS. Then RS is there. You know, you can say no, this RS is now RP, right? They are in parallel, right? These are in parallel now, right? You could say RP, but this RP is the same RS, okay? That's what I meant. Then this thing is, there is no change here, okay? RL is RL. That's how you change the voltage source to current source and vice versa, okay? This is very important. Next question. Now we talk about equivalent circuit here. Suppose you have a big circuit, right? You have a big circuit. You have tons of you have a lot of components here. You have, I don't know, How many resistors are there? There are too many resistors, too many capacitor, too many inductors. It's very complex circuit, right? It's the big circuit. Okay. Now you want to deal with this guy. Okay. So you are getting some voltage out of it. So from this circuit, you want to measure the voltage here, A and B. Okay. It has current, current source here. You have current source. You have current source. You have voltage source. It's a very messy circuit. A lot of stuffs are there. Too many resistors, maybe hundreds of them. Capacitor, inductor, and too many, could be different current sources there, different voltage sources there. Then from there, you got two terminal out of it. Okay, you got A and B. So how do you find the potential difference between these two guys? Okay, because this guy is too messy, right? So you can use some kind of trick. So that trick is called Thevenin's theorem and Norton's theorem. So what does Thevenin's theorem tells us? We can replace entire network. Remember, we have the entire messy network. This messy network, we can replace this entire network by an equivalent circuit that contains only an independent voltage source in series with impedance. So this is what it means. So I can replace this guy by one voltage source. This is my VTH. I call it V Thevenin. This is called RTH, R Thevenin. So this guy is this guy. This is AB. This is my AB. That's what Thevenin says. I can replace this guy, entire thing, by just these two guys here. These two guys in series, right? Remember, this VTH and RTH are in series. You can replace like this. That's what Thevenin says. On the other hand, what Norton says is this. So what it says is, what Norton did is just give me the proper word. Transform, right? He transformed this guy to current source. That's all. So remember we talked about current source and voltage source before, right? See the transformation? So if this is voltage, if it is Thevenin, right? Thevenin said this. I can replace that guy by this. That's what Thevenin says, right? But the Norton said, what Norton said is, okay, I can replace this guy by this guy. That's what Norton said. That's the only difference. This is Norton equivalent. This is Thevenin equivalent. That's the difference between Thevenin's theorem and Norton's theorem. Okay. So when does this Thevenin theorem, for instance, useful? Same applies to Norton theorem also. So I just mentioned it here I wrote this for the Thevenin's theorem. Thevenin theorem is especially useful in analyzing power system and other circuits where one particular resistor in circuit called load resistor is subject to change. Okay, suppose there is a resistor here. So sometimes this is 2 ohm. You want to replace that guy by 3 ohm. You can test maybe 10 ohm, right? You keep changing this resistor here. Okay, so this resistor is called load resistor. There are too many resistors inside the circuit, right? This is the big circuit. There are too many resistors, capacitor, I don't know, whatever there. So you don't care about this. But only thing is that the resistor here, you want to change, keep changing and see the behavior. I don't know, there is some kind of thing that you want to study. You're a scientist, right? So this resistor is called RL, load resistor. You want to find the current through this resistor or voltage across this resistor, okay? So that resistor is called load resistor. Again, this is the Thevenin and Norton equivalent. So this is the entire circuit. You have this, then Thevenin is this, Norton is this, or you can say this way too. So this is the entire circuit. You can represent this guy, which is Thevenin equivalent. This guy is Norton equivalent, and they're interchangeable, that kind of thing, right? Let's do one problem. So which, let's say how to figure out, let's start with a simple thing, okay? How do you find the Thevenin equivalent of this guy? So suppose, remember this is the messy circuit, but it doesn't look like as messy, right? We are just starting with the very simple circuit. So now this is the circuit you want to replace this guy by this. RTH and VTH. And this is your A, this is your B. So you want to replace this circuit by this circuit now. Okay? Use the Thevenin for this one. So let's find RTH and let's find VTH. How do we do that? Okay? To find first of all, let's find RTH, then we'll find VTH. How about that? Let's do that one at a time. So to do that, you have to, how much time do we have, guys? Oh.
Yeah, I think we're actually out of time.
Yeah. Let's do it next time then. Unless you have any question, I'm done for the day.